Well, moving forward, Tomas Mikolov is the scientific specialist of the Czech Robot Techniques, Informatics and Cyber Technique, and worked to create the set of algorithms which are capable from the text corpus creating the vector words. Today he's going to talk about the projects of mathematical models development, which are in the perspective going to be the foundation. We'll adapt, we'll learn, and we'll develop without supervision.
Hello, Thomas. You're welcome. Do you hear us?
Hello, hello. Can you hear me?
Yeah, you may start. Thank you.
So can I start with my presentation now?
Yes, you can.
Okay, great. So thank you for the introduction. And I think there was some issue about switching the language to English, but I hope that that's working fine. So I'm gonna start talking. My talk will be about more like research than applications. Concretely, I will be talking about complex systems for artificial intelligence research, and why is it actually an interesting topic if you are a researcher and you want to discover something new. So as for the inspiration or motivation, you can think of the deep learning today being inspired by neural networks and how the brain works and all these things that you probably did already hear many times about, which I think is completely fine motivation. And now there's tons of very interesting applications of deep learning to say a language or like computer vision and speech recognition or this drug discovery that we did see in the previous presentation. There's tons of very interesting and impactful applications, but at the same time, as a researcher in the AI field, I was working myself on neural networks for quite a while, and even before this word to vec that was mentioned in the introduction, I developed recurrent neural language models, which were like very successful at their time. It was one of the first results of deep learning that actually did work in practice. Did work better than simpler models or like baselines by a significant amount. So I think that the current paradigm in AI, which is supervised learning and deep learning, that's all fine if you care about building, for example, startups that can provide some quick value to the world. But as a researcher, I think it's not the end of the story. We don't really have smart machines at the moment. We don't have computer intelligence, and there seems to be something missing. And if you speak with people who did spend decades working on machine learning, you will probably hear similar opinions quite often, that there still seems to be something that we need to discover. So another actually. Not to try to somehow describe the structure of the brain as people in neuroscience are, for example, trying to do, and in some sense, even artificial neural networks are trying to copy this, but the other way around. We can see the intelligence that we people have as a property of evolution, because intelligence didn't always exist, and it happened to kind of emerge through evolutionary processes. And now we can actually model mathematically these processes that can create complex structures like our brains or our memory or our language or our intelligence, or basically even the life forms. We can find the mathematical basis for this. Maybe that can be a way how can we actually progress towards AI that would be of a different type than the current machine learning, that would be much less supervised, that would be not doing just a single thing that it was trained for, but something that can grow in complexity, that can evolve, that can do new things, more complex things than we originally did have in mind when developing it. So that's kind of like a high-level introduction. We did even write some paper years ago about these ideas, where we actually give some examples There we have a simple language game that people can learn very quickly to play, where you control some robot that sees something and is supposed to pick some objects and move them somewhere else. It seems quite trivial. Of course, the complexity increases once you realize that the robot doesn't understand English in the first place and has to learn the language through playing this game. So if you would translate all this to, say, Chinese or some language that you don't speak, and suddenly you would realize that playing this game is not so easy, but at the same time we did do some experiments with people, and people can actually learn from problems of this type or from situations of this type. You would figure out how to use some simple Chinese language, for example, simplified for these tasks from like playing games of this type, like for maybe dozens of times, maybe hundreds of times. But the current machine learning doesn't really have tools to deal with this, because you don't really have explicit supervision. You don't really know what to do. You don't have any database of perfect decisions that you should be doing. It's a bit close to reinforcement learning, where you're supposed to build some computer program that solves the task, where you know what is a failure and what is success, but you don't really know which actions lead to some rewards in the distant future. While there are these similarities, it's not exactly the same, because often in reinforcement learning you are solving a problem there, you just solve a task and you just stay there, and you, for example, build a machine that plays chess or some simple game and just does it forever. So the complexity is limited this way. On the other way around, we did think that if we deal with language, then there would be this possibility of having unbounded complexity, because you can always add some new words to language, new ideas can be expressed by new combinations of words, and so on. So this is still like high level goal, because nobody knows how to solve problems of this sort. We know that people can do it. We know that machines can't do it. Now the question is what mathematical models would be suitable as learning models for representing language learning systems. Well, of course, we can think of the breakthroughs in natural language processing that happened over the last decade, like neural networks. I was working on it myself, so this is just a graph of perplexity, which is the measure of quality of language models over some standard benchmark Penn-tree bank, and you can see actually that there was already like this huge improvement around 2010 to 2012. Where actually like neural networks started to finally work on language modeling, and state-of-the-art improved by quite a bit. And since then, we have mostly, from my point of view, we are like mostly observing the progress by seeing larger models trained on more hardware with more parameters. And there are still some new architectures that are very interesting, and there's some nice progress on it, but it seems that we are making incremental progress, and again, just taking neural language models for the task that I was describing on the previous slide is not gonna solve it. So what can we actually do to create some sort of like intelligent language models? Is it enough to just increase the size of the training sets and use more data, or do we actually have to do something new? Of course, like we don't really know the answer, because we don't have any perfect solution yet to language modeling. I'm on the side where I would say that just bigger models and more data is not going to do it. It can create, or it does already create, very interesting applications, but it's not the end of the story. Here's just an example that I did find somewhere on Twitter. It looks really cool. Like you take a neural language model, you show it some piece of text, which is this introduction in the beginning, like the first two paragraphs, and then you let it generate the continuation. and actually it works much better than if you would do the same like some 15 years ago. If you would do the same with Engram models, which were the state of the art, then it would be like totally nonsensical. While here you can see that neural networks can stay on the topic and even like discuss somewhat like what the author did expect. So it really looks very impressive, but I think that people are mistaking here things a bit, because these language models were trained on huge amounts of data sets, and so like sooner or later the story will turn into something weird. Actually, even the further continuation of this would suddenly like turn into some Harry Potter story and so on. There's issues that the language models do have, and I would say that there's also like this illusion of intelligence just because a parrot says that it's intelligent, or a computer program copies a sentence from a training set that says that it has a soul or whatever. Or consciousness, that doesn't mean that it's true, and you can have like trivial examples of this sort that just hard code some sentences into a computer program, and that doesn't mean that it's the computer that produces these sentences, but it's actually the humans. So back to this example, it's important to realize that the logic in this text heavily depends on what was typed by the humans. Basically, the intelligence is hidden in the training set, which was produced by humans. So it's not as easy as it seems, and we will certainly observe many cool applications in the future of language models. I can totally see many of them. But the current technology, from my point of view, is not enough to take us to AI, and we can just name the problems. Like there's an issue with memory once you start talking about some concrete thing for a longer time, and then you let the language model to generate the continuation of text after like a couple of dozens, or at best hundreds of words. It will just drift to some different topic, and the language models are fixed after the training phase. They don't learn anything anymore, and just stay static, and that's not how the language understanding works. In humans, we keep changing our memory as we live, as we process the data. We keep updating our memory, creating memory structures. That's all the things that the current paradigm in machine learning doesn't really know how to deal with. So back to the main story of my talk, complex systems. Also, it sounds complex, but they are actually quite simple. Can be a solution to this. It's systems where you iteratively apply some simple function again and again, and you observe some evolution of this dynamical system in time. There's a lot of phenomena that can be seen as complex systems. You can see language as a complex system. You can see even the whole universe actually as a complex system. There was a number of physicists who did study the evolution of universe and even self-organization of the matter, by treating universe as a complex system. There are people in the computer science who study models like Sora automata that we will see in a while. That again can be seen as complex systems. Of course, now the question is, why should we care about this new direction? Or new direction, it's quite an old one, but unexplored direction in machine learning that would be actually trying to build AI around this idea of emergence of patterns in evolving systems. Well, if we want to actually have a system that can reach arbitrary complexity without being explicitly programmed for it, then actually this may be necessary. There's also a community of artificial life that is studying these complex systems, where actually you see that artificial intelligence may be just basically a property of artificial life. So these are all interesting things. The issue is that once you start actually digging into this, you will realize that there was a lot of very smart people working on these ideas before, and they did run into many problems. Just to name a few, if you want to start measuring actually complexity, if you have some of these dynamical systems where you can create some structures and you can possibly make some time diagrams, space-time diagrams of evolution of some of these systems. Then how would you actually decide which system is complex or which is more complex than the other? I have 3 examples of some kind of fractal-like shapes. Some of them are simpler, some of them are more complex from our intuitive point of view. But once you actually want to measure this using, for example, minimum description length, also known as Kolmogorov complexity, you will actually run into issues that all these patterns can be generated by a rather short program, and there's not that much difference actually in complexity from this point of view. So there are some advantages, but there certainly are significant disadvantages. The other issue is that it's not even computable. The Kolmogorov complexity. So it's not very practical to think in this direction. Of course, we can take information theory from Claude Shannon, but basically we run into very similar problems. In philosophically speaking, maybe the amount of information in the universe is fixed, but all the complexity that we see around ourselves may be just kind of illusionary to some point. Or we can just say that maybe the complexity metric should be different. There's a pretty nice book written about it by Murray Gell-Mann. It's called The Quark and the Jigger. So I'm not going to discuss all these complexity metrics, but we did take them as inspiration for our further work. Some of these ideas are what is the time needed to compute the structure, or we can try to measure the number of identifiable patterns, which would be more like a memory complexity of some compressor. So there are other approaches how to measure complexity. I would say all of them have some issues, some drawbacks. Usually they are not really computable in a strict sense. But we still did take them as inspiration, and we started working on some of the simplest systems that fall into this complex systems category, which is called silver automata. It maybe looks very simple to you. Many of you did see it in computer science classes a long time ago. Just to quickly describe, you have some rule table that just says what will be the evolution of the cells on some one-dimensional tape. Time is shown here on the y-axis, so you go from up to the bottom, and you always recompute the state of the whole tape using the rules from the rule table, and just by iteratively applying the rules to some very simple starting state where you have one block in a state 1 and everything else in state 0. You suddenly start observing some emergence of some structures, and it seems to be going indefinitely long. So that's the exciting property, that you can suddenly start building something out of almost nothing. So this has been studied by Stephen Wolfram and many other scientists who did try to identify different categories of these complex systems. They are kind of the boring ones, which are the top 2 figures, where actually you don't really see much of computation going on either. The computer stops very quickly in some empty state, or it just enters some very trivial loop very quickly. Then there are the more interesting categories on the bottom right. There's the chaotic category, which seems to be going on forever while creating and destroying patterns so quickly that there's nothing really much observable. It's looking close to some random number generator. And then there's the bottom left figure, which was considered to be the complex one by Wolfram. Then it's somewhere between the regular and the noisy behavior, where it seems that there are some structures that are appearing over time. Other famous example is Game of Life, which is basically the same thing, just in 2D. So instead of 1D tape, you have this 2D grid, and then time is shown as time now. So you see that there's, by just applying some simpler rule, again and again, you seem to observe some moving shapes over this grid. which are called gliders that can collide in some ways and create other structures. So this actually did catch attention of many mathematicians, and there's a lot of studies in this area. We try to work on in this direction, but we wanted actually to find complex systems where actually the complexity, from our human point of view or close to it, would be increasing as fast as possible, so that we would not need to wait for trillions of years for our game of life to create anything interesting. But once we started maximizing the complexity by using this information theoretic point of view, by building a compressor, which is just approximation, of course, of the information content, but by just compressing the states of these automata and finding the ones that have the largest compression length, then we did find just these noisy automata. No matter how many states we did use, it was just looking like some sort of noise, and there doesn't seem to be any evolution. You don't really see any patterns emerging here, and if you would simulate this for 1 million years, then likely it would not really create anything that would resemble our universe or our life or our intelligence. So we did take other approach where we there were two projects that I will describe. In the first one, we used a neural network that was trying to predict the state of a cell given its neighborhood. So it's basically some sort of simple compressor. But now we actually wanted the compressor to work well across different time regions. So we wanted increase in this compressed length, increasing complexity, but at the same time, the objective function was not just increasing compressed length, but also how good the compressor is across different time periods. So, for example, if you simulate these automata for thousands and thousands of time steps, there should be some similarities across different times, so that patterns that emerge should be somewhat persistent. They should stay for a while in the state of the system. And then when we were maximizing this metric of complexity, then we did find that the automata that did have high complexity were suddenly looking much more interesting from our point of view. It was looking kind of like these gliders in Game of Life, while Game of Life was actually manually hard-coded, designed. Then we did find actually these many different systems automatically. So that's actually what is exciting about our work, that we actually did not design these systems ourselves, but we did just design the complexity metric, and then we did find these different behaviors automatically just by sampling a lot of automata from this space of many different 2D automata with 3 states. And then we did find all these interesting behaviors automatically as byproducts of searching for complexity. There was also another approach that I will quickly describe. It was more mathematically oriented or motivated, and that's where we actually see these automatons as some sort of computers, and we measure how long does it take for this automaton to finish the computation, which we think happens once the automaton starts looping. And the transient is actually the number of time steps that it takes for the automaton before it actually starts repeating some state. So it's basically the length of the computation in some sense. We can see it as that. And then the idea was that the computers that or automatons that very quickly converge to some stable state or periodic state will have short transients, and the transients will not even grow with the size of the automaton. We can be making these grids larger and larger and see how quickly do transients grow with increasing size of the automaton. And that's what we did actually observe. The first class that we did identify was this bounded class, where actually the transients are bounded by some upper limit. And the automata of this type are the boring ones that actually start or end very quickly the computation by entering some stable state. There are also the automatons where actually the transients would grow logarithmically with the size of the automaton, and these were also like the boring ones. There would be a little bit of computation, but still the automaton would very quickly end in some state that was not interesting. Then there was this linear, or like maybe you can say polynomial class, which was the most interesting one, that corresponds actually very closely to that complex category of Stephen Wolfram. And finally, there was this exponential class, which is more like this noisy class, where actually the transients grow like super quickly, like exponentially with the size of the grid. And that seems to like identify quite well the automata that don't really create any stable patterns over time. So the interesting thing, again, is that while Stephen Wolfram did actually identify his classes by actually looking at all these automata and studying it manually, we did develop an automatic metric of this complexity, or in this case it's a classification into these several classes that can be applied to any other automata. It doesn't have to be just these elementary cellular automata, which we know that there's like 256 of them, but it can be, say, 2D automata with 3 or 4 states per cell, which there's a lot of like a huge number of them. It's not possible to study manually all of them, so we could actually apply this classification to more complex automata. This is what we did find, actually, like just some examples of automata that are in this polynomial class, which we consider the interesting ones. And you can see that again, like there are some propagating structures that interact in some way and are creating some shapes and patterns. And again, like it's quite diverse in the behavior, because we didn't actually hard code any of these. We did just find automata that are in this interesting region, and it's looking like quite interesting from the philosophical point of view. Maybe this is kind of like close to some sort of like artificial universe that just evolves in these mathematical structures. Of course, like this is not the end of the story, because that's actually not our final goal. We don't want to just create some artificial universe. We want to create artificial intelligence. So we would like to also, like in the future, like follow up on these projects and connect these evolving models to something useful. In fact, it's not that far from machine learning as you may think, because these automata, as I'm showing them here, they can be actually represented equally exactly the same by using recurrent convolutional network with stepwise activation functions and no inputs, no outputs, where we basically just observe what is happening in the hidden layers. Like a typical neural network will have like a noisy behavior in the hidden layers, while we are aiming for developing some models. It could be possibly even neural networks in the future, who knows, where actually if you don't really show any input or supervision on the output side to the model, it can still do something, and it can evolve unsupervisedly, just using its internal mechanics. So you can think of these models as possibly like some different or like some specialized types of models like neural networks that will have this property of being able to support this emergence of patterns over time, support the possibility of evolution, which is something that typical randomly initialized neural network just doesn't have. That would fall into this noisy category that you can just run it forever and it will never create anything. So that's like this very, very like ambitious and risky like approach to developing AI using these ideas like evolution and emergence, and I find it very exciting because it's a very much underexplored at the moment, and who knows what can we actually discover, because like it's very exciting, because there are very basic questions that still are not answered. So thanks for the attention, and I don't know if we have time for a few questions.
Thank you, Thomas. Thank you for your progressive research. I hope it will be very useful in the future and right now. AI systems are increasingly being integrated not only into business processes, but also into daily use. So in your point of view, what best practices can you recommend for choosing a complex system for an AI project?
Complex system for an AI project. As I was describing it, it's very much research at the moment, like basic research. So if you think about practical applications in daily life, then I would say what we understand quite well, and that would be supervised learning. That would be certainly like my first choice. Like if you want to solve some problem, like translate languages or recognize objects in images, then supervised learning is what works, and that's what I would choose. So I'd say complex systems for artificial intelligence research, that's more like a basic research direction. So it's really like motivated to create a technology maybe like 10 years into the future. I was giving that example in the beginning with neural networks. That it also exists since the 80s, but they were not used because people didn't really know how to train them well, and it didn't really work on many problems. And then there was suddenly, like 10 years ago, like this huge progress, and I was actually part of it because this huge jump in the performance on the Pentry Bank language model, and it was actually my work. So you know, like there's always this value in the basic research, but it takes time to show. And at the moment, if I would want to build a practical application, I would not like base it around the complex systems. That is aiming for the research and for people who want to develop something that doesn't exist yet.
Tomas, thank you very much for your report. It was nice to hear you, to listen to you. Thank you very much, and best wishes, and bye-bye.